The next problem is chapter 14, number 1. It says, what change in pressure occurs in a party balloon that is squeezed to 1/3 its volume with no change in temperature? That is Boyle's law, where we have P1 times V1 equals P2 times V2. This problem says no change in temperature. And I left some space there, you'll see in just a moment. So it occurs in a party balloon and is squeezed to 1/3 its volume. So 1/3 its volume. Well, the equation needs to be correct, left and right. This is the original pressure, original volume. This one here is the final volume, so we need to have the final pressure. So the pressure increased 3 times. And of course, we notice that as we squeeze a balloon, the volume gets smaller, but of course the pressure gets larger. The next problem is chapter 14, number 4. It says, estimate the buoyant force that air exerts on you. Parentheses, to do this, you can estimate your volume by knowing your weight and by assuming that your weight density is a bit less than that of water. It says in first word for this problem is estimate, which means that the answer I'm going to come up with depends on what my weight is and perhaps some estimations that I'm making. So that means that you or somebody else may not come up with the exact same number I come up with, but we should all come up with the same ballpark figure. Okay, so first, my mass is 90 kilograms, and this would be me or a Norman peasant standing on a scale. So next I'm going to figure out, well, my density is roughly that of water. I know it says a little bit less here, but let me just use that. It's roughly that of water, which means that my volume is also 90 liters because there's 1 kilogram to the liter for water. Now this is my volume. As I'm submerged in air, so to say, I'm sinking in the air as low as I can. Obviously I'm not floating. The displaced volume of air is the same as my volume. So I displace as much volume of air as what my volume is. So air V equals 90 liters. Now I'm looking up how much mass of air that is, or I'm going to compute that. So I'm looking up what the density of air is. So density of air equals 1.29 kilograms per cubic meter. That's a relatively small density. Usually when we had the densities for solids and liquids, we were in the neighborhood of a few thousands kilograms per cubic meter. Here we're at only 1.29 kilograms per cubic meter. Makes sense. Air has relatively little mass. Still, that's 2.5 pounds for a cubic meter, or roughly 30 cubic feet, top of my head. Okay, so next thing is that the mass of the air that I'm displacing is the density times the volume. So 1.29 kilograms per cubic meter times 90 liters, but my volume units need to match, so I'm going to have 0.09 cubic meters because there are 1,000 liters in the cubic meter. So the air that I'm displacing comes out to 1.29 times 0.09, which is around at 0.1 kilograms. And multiplying that by 9.8 meters per second square gives me 1 newtons, which is the weight of the air that I have displaced. That's also the same as the buoyant force. So this one here is the weight as well as the buoyant force. So 1 newton, and when I divide that by the conversion unit of roughly 4.5 or 4.4, I come up with 0.2 pounds. And keep in mind that it is estimated. That is the buoyant force that the air exerts on me, which is also the weight of the air that I displace. So compared to my 200 pounds of weight, that's relatively small and probably negligible. The next problem is chapter 14, number 7. It says, on a perfect fall day, you're hovering at low altitude in a hot air balloon, accelerated neither upward nor downward. The total weight of the balloon, including its load and the hot air in it, is 20,000 newtons. So the weight of the balloon is 20,000 newtons. What is the weight of the displaced air, and B, what is the volume of the displaced air? Well, A, the buoyant force that is produced by the air on the balloon has to equal the weight, because the balloon, as it says, is hovering, and then they added it's neither accelerating up nor downward, so the two forces have to balance each other. So the weight is pulling down at 20,000 newtons, and the buoyant force is pushing up at 20,000 newtons. So that's part A. Part B says, what is the volume of the displaced air? So since the weight then of the displaced air is also 20,000 newtons, I would have to divide that by the density. So volume equals the mass of the air, which is 2,000 kilograms, because a weight of 20,000 newtons is divided by 9.8 or 10, so it comes out to 2,000 kilograms, and then needs to be divided by the density of air, which is 1.29 kilograms per cubic meter, and then 2,000 divided by 1.29 on the side comes out to 1,300 cubic meters. This problem is a little bit different than the last one, because here we have a floating balloon, and something that is floating will displace as much air as it weighs. While in the last problem I was submerged in air, and when you're submerged you're displacing as much volume as your own volume is, just like Archimedes' principle says. Okay, next problem is chapter 14, number 8. I'm going to do that as quickly as I can to squeeze it into these 10 minutes. How much lift is exerted on the wings of an airplane that have a total surface area of 100 square meters when the difference in air pressure below and above the wings is 4% of atmospheric pressure? So the force comes out to the atmospheric pressure times the 4%, so 0.4 times area. So atmospheric pressure is 100,000 pascals times the 4% times 100 square meters, and that comes out to 400,000 newtons, or 400 kilonewtons.